Lab 3, Black Hole Orbit. This week's lab presented the problem, can we find the mass of a black hole by observing the motion of a star orbiting the black hole? Through the help of VPython, I was able to set up a program which I found the mass to be 2.1791 e to the 31 kilograms. In addition, I compared Fnet to its components to the rate of change of momentum and its components. I also discussed the possibility of another quantity of mass that would fit the given conditions. To start, let's talk about the present physics principles. The first being Newton's first law. An object moves in a straight line and at constant speed except when it interacts with another object. The circular path of the star indicates the presence of a force and is the first step stating the existence of the invisible black hole. Our next principle is Newton's second law, which when manipulated gives us the momentum principle, which if taken in its derivative form tells us the time rate of change of an object's momentum equals Fnet. Our last principle is Newton's law of gravitational force, which states the force of attraction amongst objects. The gravitational force is directly proportional to the product of the masses of the objects and inversely proportional to the square of the distance between them. The gravitational constant g is 6.67 times 10 to the negative 11. This principle is key to the experiment because this is the equation I manipulated to solve for the mass of the black hole. To set up the experiment, we were given some initial conditions. A set of data plotting the star's motion around the black hole, mass of star, the time step of 1 day, and the location of the black hole. Other initializations include defining the black hole in our computer code, as well as defining our gravitational constant and setting my start time. I also created arrows to visualize Fnet and its components. Next, you see the highlighted portion of code importing the data from our CSV file. The first while loop then takes in the data and computes the velocities of the star as it travels around the black hole. Our second while loop contains the bulk of our process. Our first step is to find the initial and final velocities, which we calculate from the given position data. I then took these values of velocities, multiplied them by the mass of the star to find initial and final momentum. Building on Newton's second law, I used the derivative form of the momentum principle in my code to define Fnet. Recall that the change in momentum over the change in time equals Fnet. I further used the momentum principle by breaking both Fnet and dPdt into its parallel and perpendicular components. The principle states that F parallel and dPdt parallel are equal, as well as F perpendicular and dPdt perpendicular. This is crucial help to my experiment, as you will see. I first calculated dPdt parallel, which is defined as the magnitude of the change in momentum divided by time multiplied by p hat. My p hat, which is the direction of momentum, was calculated by taking the initial momentum and dividing it by the magnitude of momentum. This leaves us with defining dPdt perpendicular, which formally defined as the magnitude of momentum times the rate of change of direction. Although dPdt perpendicular has too many unknowns to directly define, I used what I knew of the momentum principle and defined dPdt perpendicular to be the result of subtracting dPdt parallel from dPdt. Finally, I completed Newton's momentum principle by stating the components of momentum are equal to the components of Fnet. I then entered the code for calculating the mass of the black hole. I calculated the distance between the point mass of the star and black hole, defined it as r, and plugged it into my rearranged equation of Newton's gravitational force, solving for the mass of my black hole. As well as putting some final touches in the code, which I update the position and velocity of the star, adjusting my arrow scale so you can see optimal visibility of the arrows of Fnet and its corresponding components, as well as advancing the clock and my data points and printing the quantities that I want to know. Now let's see the computer module. As you can see, there are 3 arrows present on the star. Yellow is Fnet, blue is F perpendicular, and black is F parallel. Both the yellow and blue arrows change in size as they are larger as they approach the black hole and smaller as they move away. This demonstrates the gravitational force increases with proximity, which follows Newton's law of gravitational force, whereas the black arrow, F parallel, stays constant size because the star is orbiting at a constant rate. And these are my results. I found my total time, my magnitude of Fnet, magnitude of F parallel perpendicular, as well as the mass of my black hole printed out in my VPython code. Now for the questions. What does it mean? How do Fnet and its perpendicular and parallel components differ from dPdt and its perpendicular and parallel components? First of all, dPdt and Fnet are calculated differently even though they have the same numerical value. Fnet is calculated through Newton's gravitational force law, and dPdt is calculated from the derivative form of Newton's second law, also known as the momentum principle. Another difference is that Fnet is the effect another object has on our system. It's an external characteristic, whereas dPdt tells us the motion of our system and is an inherent quality. What if? What if all the data remain the same? Could we possibly find a new mass of a different quantity for our black hole? If the data points given in the CSV file stay the same, there is no other gravitational force calculating into the mass of the black hole, then the mass we found is the only mass that will fit the data. The only way to find a different mass would be a similar path of orbit with different position points. This would yield a different mass. Thank you for listening.